just going out there and taking images of every exoplanet that we know about. So to start out by illustrating this, to illustrate this with a sort of kind of real world example, pretend that this diagram shows you the pupil of a 6.5 meter telescope. This is the same size as JWST or the Magellan telescopes. And assume for the time being that this is perfectly smooth. There's nothing wrong with it. It has no aberrations on its surface. So I know it's early, but I have to use Fourier transforms because we're talking about imaging and there's nothing I can do about it. So the image formed by this telescope is the modulus squared of the Fourier transform of the aperture function. So that the white pixels are 1, the black pixels are 0. Take that Fourier transform and square it, and you get what's called the PSF. And you probably all know this. This is the airy pattern. It has the airy disk surrounded by airy rings, and this is what a perfect image on a perfect telescope will always look like. And just to make sure that we're all on the same page, this is what it looks like when you take a line out. The full width at half max is roughly lambda over d. There's a few small scaling factors there that depend on the details of the aperture, but we treat lambda over d as the fundamental unit in diffraction limited imaging using the Sparrow criterion. And so I'm going to refer to lambda over d several times. So I want to fix that in your head what that means. It's the full width at half maximum of that central peak. So if we use a telescope, a perfect image like this to image an exoplanet, how faint does that exoplanet, how faint will it be? In other words, what contrast do we have to get to? So you can calculate the contrast of a planet in reflected light. So now I'm talking about light that's bounced off the planet from its star and then come towards us and been collected by the telescope. And the contrast is the ratio of flux from the planet to the flux from the star. And already you can tell that this is a horrific problem because the scaling factor is 2 times 10 to the minus 9. And then it goes as the radius of the planet over the separation of the planet squared. This AG is the geometric albedo. This is a way to quantify the amount of light that hits the planet that actually reflects off the planet towards us. It's a function of wavelength. And here I'm using phi as the phase function, which captures the fact that we never actually see this image of a planet. If that image is when the planet is directly behind the star. We actually are going to take images out here where you're only seeing some of the planet. So that quantifies the amount of light that is coming from the planet. And if you do the math for an Earth, it's pretty simple. Radius is 1, separation is 1. The geometric albedo in the visible is roughly 0.25. We'll use a phase angle of 90 degrees. This is more or less 90 degrees. This is from Apollo watching the Earth rise over the limb of the moon. And at 90 degrees, this phi is about 0.32. So you plug all those numbers in and you get 1.5 times 10 to the minus 10. So it's 10 billion times fainter than the star. So now let's combine these two things, that airy pattern and this 10 billion times fainter image of Earth. And so let's try to look at a G star, a G2 star, just like the sun at 10 parsecs. And at that distance, it's going to be roughly fifth magnitude. 1 AU is 0.1 arcseconds, or 6.3 lambda over d. And a good scaling factor for this to think about, you don't have to do this, but imagine plucking a hair from your head and holding it out at arm's length and squinting at it. If we all did that, the average would be about 1.0 arcseconds. That's how wide that hair is. So we're talking about 10 billion times fainter, 1/10 of a human hair from a star. So this is what we call hard. And in this image, which I have scaled to be a 1-hour exposure of this G2 star with this, remember, perfect telescope, and added photon noise. I actually added a little read noise, but it doesn't really matter. And I put an Earth in there. So this image of Earth is buried under those airy rings. And of course, you can't see it because the airy rings from the star are swamping it. And since I've assumed a perfect telescope, you might ask, why not just do PSF subtraction? You know the airy pattern, just subtract those rings out. Well, you're left with that photon noise. It's still swamping the planet. You cannot see it. So the number one thing we need to do this, this little science project of imaging planets like the Earth is a coronagraph. So we need a way to block the light from that star. The simplest coronagraph is to get Olivier Guillaume to put his thumb over the star. That'll work. You could wait for a solar eclipse. You could fly Cassini out to Saturn. And that's actually the the perfect example. We're using something to block the sun so that we can see an Earth-like planet. This is a 10 to the minus 10 image of a planet next to a G-star. Of course, none of those are really going to work for us, so we need something a little more complicated. This is the basic Lyot coronagraph architecture. So in forming that image of the Airy pattern, we went from here, skipped all this stuff, and went right over here to the detector point. So the coronagraph adds all of this stuff in the middle. So what we do is we take an image of the star and put opaque solid disk right here in the middle that blocks this starlight. So behind the disk, it looks like this. There's just this faint ring of starlight that goes through. And then we make another image. This is called a pupil image. So it's an image of this aperture. And there, now because of this disk, the diffracted starlight, it goes to mostly these two bright rings. And so if we put in a slightly shrunken copy of this pupil and block that light, we've removed most of the starlight from the image. And then we then take another, then we finally form the focal plane. And on that focal plane, we should have an image with no starlight in it. Now, this is a very rudimentary coronagraph, and I'm not actually going to go into much more coronagraph theory today. You should know that we are well beyond this basic architecture, but this is the basic idea that most coronagraphs are based on. So I'm next going to put in our little toy example of a G2 star at 10 parsecs with 1 hour exposure, an ideal coronagraph. This is a mathematical trick that simulates if this all worked perfectly, and boom, there you go. There's Earth. At 6.3 lambda over G from the lambda over D from the G star. If you got rid of the starlight, this is easy. This is a 1 hour exposure in V band. And so this is kind of an important thing to keep in the back of your mind, that this isn't actually impossible from first principles. We can see Earth at 10 parsecs. So this is the point in a TV show where the narrator says it wasn't an ideal coronagraph and it wasn't an ideal telescope. So moving on in the episode, the real problem is we have real optics. So imagine that on that primary mirror, there's a polishing error. And this is just because manufacturing never works as well as you want it to. And that polishing error, for the sake of argument, is this contrived cosine wave across the telescope. And in this example, we're going to call this 1 picometer semi-amplitude. So it's going up and down by 2 picometers peak to valley. So a quick aside on picometers. You're hearing people like me talk about picometers a lot because this is the stability we think we need in space telescopes. We throw this word around a lot without really talking about what it means. We coat our mirrors in silver atoms. We use silicon atoms. Their telescopes are made out of big atoms. Those atoms are 320 picometers across. So when we say that the 1 picometer sine wave, I just want you to keep in mind the amount of the level of precision that we're invoking. So we have this cosine wave. It's 1 picometer or 1/320th of a silver atom. So here's another Fourier transform. So this, instead of the PSF, we now have the intensity distribution in the focal plane is the modulus squared of the Fourier transform of the aperture function times e to the I phase. So this is the complex wave expression that accounts for this aberration on the primary mirror. And this is what you get. And this is again assuming an ideal coronagraph. So now we have a non-perfect primary mirror, but a perfect coronagraph. The image of Earth is still there, but what are these? Anybody know what these are called? These are what we call speckles. And you'll hear us talk about speckles all the time. So, and I'll leave this as an exercise for the student. If you plug in a sine wave or a cosine wave for this term with a very small amplitude, smaller than the wavelength, then you should know I'm leaving out a bunch of scaling factors because they would just be noise. And work this out, you will find that a cosine wave like this always creates 2 copies of the PSF, just like that. And it always will look like the image of a planet, which also is the PSF. So as you can imagine, if you took this image, you'd be, I've got 3 planets. This is really exciting. Look at this amazing system. So these are the primary source of noise in high contrast imaging is these speckles. So this is a key takeaway to know about high contrast imaging. Is that a Fourier aberration, so the sine or a cosine in a pupil plane will produce a pair of symmetric speckles. And in any other plane in the system, a Fourier aberration will also produce a speckle. It won't necessarily be symmetric and it's more complicated, but this is a very general result. And the key scary thing is it will look just like an image of a planet. So you're going to have these speckles running around in your focal plane, and you have to be able to decide, is that a planet or is that a speckle? Now, this is obviously a very contrived example. We don't polish in, I don't know of any mechanism that would polish in a perfect cosine wave into a mirror. So this is a real mirror. This is a post-polishing interferometric map of the Magellan clay primary mirror. So this is a 6.5 meter piece of glass. This was done at the University of Arizona Mirror Lab. And so note the scale here. This is nanometers. The total RMS of this image is 12.52 nanometers. That's actually a really good optic. Remember, this is 6.5 meters across. So there's a scaling factor that tour guides at the Mirror Lab use, that if you took a 6.5 meter mirror and blew it up to be as big as the continental United States, the largest feature on that would be less than an inch high. So that's the sort of scale of how smooth the Mirror Lab makes these mirrors. So, and then let's just apply a basic Fourier analysis, Fourier series. So all I'm showing here is I want to motivate the idea that this is sines and cosines, right? The complex exponential. This map can be deconstructed into just a summation over a bunch of sines and cosines, which means that there's going to be a lot of speckles in the image. In fact, it's all speckles. So this is the modulus squared of the Fourier transform of that aperture with the ideal coronagraph in it. So there's no actual airy pattern. What's left here is just this swarm of starlight that is purely scattered off the imperfect primary mirror. And remember, this is 12.52 nanometers roughness. It's pretty good. So the result here is that in real optics, the final focal plane after the coronagraph, if you don't do anything else, is going to be covered with light. And you're not actually going to see a planet sitting right there. This is still factors of 1,000 or greater than being able to see the planet. So next I'm going to show you this nice movie that NASA put together to illustrate what a space telescope coronagraph would look like, just to kind of drive home what I just went through, how a Lyot coronagraph works and what that final focal plane looks like, even in space. So this is a very stable space telescope. And you have these imperfect waves coming in because the optics aren't perfect. And it goes through that imaging system that you should recognize as a Lyot coronagraph or possible Lyot coronagraph. And we'll put in that focal plane mask. We'll put in the Lyot stop, which is just kind of like a washer. It's just a copy of the telescope pupil. And the airy pattern you saw disappear in the science detector. And the key thing is the planet light misses this mask, so it goes through more or less unaltered. That's kind of a lie, but for our purposes, you can assume it goes through unaltered. But we're still stuck, even on the space telescope, because of the imperfections in the optics and all the problems that can happen in a real system, you can't see any planets. For completeness, I'll point you at, come on, I guess there. That video is available on the NASA Exoplanets website. It actually has a very nice animation, narration by Nick Siegler, the chief technologist, and there's an extended version that really goes into detail about how the coronagraph works and the science that can be done with such an instrument. So I highly recommend watching that video. So now you sort of understand how the imaging works and how the photons end up on our focal plane and what's happening to the photons from the planet. They're being covered by all of this residual scattered starlight. Well, so what? You might just assume that it's just a photon noise problem, right? That if we were purely photon noise limited, this would be the variance in the focal plane. It's just this is the flux rate from the star times the exposure time times this I, which is, remember, that's the intensity distribution in the focal plane. So this is, at any point here, this is just telling you that the variance is the number of photons that you collected. And this was that noise map I made. And so the key point here is that the limit of our ability to detect the planet is set by this variance. It's the variance of the intensity in the focal plane. So everybody's probably good at picking out these kinds of things, but guess what? This isn't what the variance looks like in a speckled image. It actually looks like this. And I know it's early, and we're not going to go through this in great detail, but I just kind of want to give you an idea of why this is such a problem. And I think this is really important for understanding the following talks, Kate's talk and Travis's talk in particular, who are going to talk about post-processing and some of the things that we have to do to deal with this problem. So this expression describes the variance as a function of time of any point in this image. it also technically can be used to describe the variance if you go in a circle centered on the center of this image. So this is sort of for completeness, the notation, remember this is the flux from the star, the exposure time. These I's are the same thing. They're the intensity distribution in the focal plane. We have to split this into the residual coronagraphic intensity plus the intensity coming from those speckles. So no coronagraph is perfect. It always leaks a little bit. So there's always some residual airy pattern. And then there's these lifetimes, which is the lifetime of a speckle from the atmosphere. If you're on the ground, this is 0 in space. And the lifetime of what we call quasi-static speckles. So these are speckles from the instrument. This is these imperfect optics that hang around for non-zero amounts of time, but not infinite. And because if it was infinite, we would just calibrate them and subtract them and move on with life, but they change. And so they have a lifetime. And this is just that photon noise that everybody kind of understands and is comfortable with. But this is the speckle noise. And this is an image of a aberrated, this is atmospheric speckles in without a coronagraph. And so you can kind of see how they're coming in and making this large collection of planets, it's a very dense system, around these stars. And this is the one that I showed you earlier that's just coming from the primary mirror. So this is really nasty. You'll notice that this has flux times flux. So that's a lot worse than just flux, right? So if you have 10 to the 11 photons, which is kind of a normal number just to throw out there, that's actually a really big noise term. It also has these two, I've separated this so that there's these two terms. There's the atmospheric speckles and there's the quasi-static speckles. And look how nasty this is. The atmospheric speckles and the quasi-static speckles are interfering with each other. That's what this means. Any residual coronagraph leak that you have is interfering with the speckles. That's what we call this speckle pinning, which I'm not going to go into, but it's a particularly nasty problem. It's a huge amplification of the variance at that point in the image because you have this interference between these different parts of the electric field. And they're all modulated by these lifetimes, which can be very big. Atmospheric speckles are sort of 100 milliseconds or less, but these can be hours, but they can also be minutes, which is a real problem because you have to have, if you want to be able to get rid of this stuff, you have to have long enough to measure it before it changes. But then by the time you've changed it, if it's only a minute in lifetime, then it's changed by the time you get around to using a correction. So the key thing here is speckle lifetimes are greater than the lifetime of photon noise. Photon noise is basically set by your exposure time, that you reset that experiment every time you expose your camera. But speckles just keep living, but they change slowly over time, so they're really hard to get rid of. So some key results here from this sort of rapid introduction to speckle statistics. These are an inevitable result of imaging with real optics. Nothing you can do about it. There's just no way we can polish optics to the level where we would have negligible speckles. Speckle noise is going to limit any coronagraphic detection attempt on an exoplanet. And there's just nothing you can do about it. And it's fundamentally different from photon. Its behavior in time is different, its behavior in space is different, and it's spatially and temporally correlated. And we learned a little bit about spatial and temporal, or especially temporal correlations yesterday. And we're just adding this dimension of it's also correlated in space. And this is bad. The correlation means that it averages very slowly. So you can't just sit there and bang away on an image of a star and hope that this goes away. The good news is this means that you can actually post-process it. It gives us a little bit of leverage to get rid of it because we can understand how our images are evolving with time. And that's the subject of some following talks. So what do we need to do to achieve high contrast on the ground or in space? So everything I'm saying right now applies to both a ground-based telescope and a space-based telescope. It's really just a question of scale. So in space, we have a much more stable environment, and we typically we therefore have a smaller dynamic range of aberrations that we have to control, and they're slower. They evolve more slowly. But you still have the same wavefront control problem in space because of those imperfect optics. So what we need is large telescopes. Large kind of depends on who you are and what you mean, but we're sort of talking about 4 meters to 40 meters. 4 meters would be sort of a HAVX class space telescope, and 40 meters is the ELT telescope being built by ESO. We need a way to block starlight. This means a coronagraph, which I sort of introduced before. In space, you can also use something called a star shade. I'm not actually going to talk about star shades today, but we should just mention that so that you can go look up what a star shade is. It solves some problems, but creates a bunch more problems. And so it's kind of a interesting competitor to coronagraphs. No matter what, you need very good optics. And then a key thing is we need a way to deal with the imperfections in our system. That's because they will be there. It's going to be in our optics, and on the ground, we have to deal with the atmosphere. So all optics are imperfect. The atmosphere exists, and all these things are changing with time. So I've mentioned this several times, this quasi-static concept for Speckles. Even in space, right? Spacecraft have to roll, they have to repoint their solar panels, they orbit the Earth maybe. All these things are causing changes in the environment of the spacecraft as different sides are being heated. Spacecraft have mechanical systems in them, such as reaction wheels for pointing. These things vibrate and causing things like pointing errors in the telescope, both from just, you can imagine, jitter, but also drifting. All this stuff causes the light path going through the telescope to change, which then changes the optics that the light is actually interacting with, causing these aberrations to change. And on the ground, we have this problem of the wind blowing the atmosphere around over our telescope, sometimes at very high rates. So the solution here is real-time wavefront control. So we can't wait for those photons to land on our focal plane. If we do that, it'll swamp our image of the planet, and we'll never detect this planet. So in real time, which means that as we're taking data, we have to be controlling the wavefront as we go. And so this is a simple cartoon block diagram of a wavefront control system, also known as an adaptive optics system. On the ground, we call these AO systems. In space, they're usually called wavefront control systems. They're basically the same thing. There's very few differences between them other than, like I said, the scale of the aberrations being controlled and the speed at which we have to control them. So aberrated light comes in. It could be from the atmosphere, or it could be from the imperfect optics. Bounces off the deformable mirror, which we'll get back to, goes into the system. Some light is split off for the science, and some light is split off to what we call a wavefront sensor. And the wavefront sensor is what actually senses how much that wave is aberrated. And then you have a control system, which job is to analyze the images or signals that come off the wavefront sensor. So it does a bunch of math, calculates a control signal that would then remove that aberration and sends it to the corrector element. This is usually a deformable mirror, just a thin piece of glass with a bunch of actuators on the back that you can push and pull on. So you put that perfect signal on there, and then hopefully what you get is, instead of these crinkly wavefronts, you get flat wavefronts when you get to the science detector. So here's a very nice cartoony video put together by Gemini to illustrate this concept going on an 8-meter telescope. An AO system is usually just an instrument behind a telescope. So what you're seeing here is that light coming in, bouncing off a mirror, going through the beam splitter. The red light is the science light. And you see this swarm of speckles, which is the seeing limited image coming in because of these crinkly wavefronts, which are distorted by the atmosphere. I call this the potato chip animation. And so now you see the wavefront sensor. And what we did is close the loop. So now we're sending these signals back to the deformable mirror, fixing it. All this is happening 1,000 times a second when you're using an AO system. And you saw this image get cleaned up and turn into this almost airy pattern, but with this swarm of speckles going around it. So that's what we have to do to clean up the atmosphere on the ground. The computer sometimes wants you to see the video again, I guess. So a key thing to know about this problem, and on the ground this is particularly important, it's also a problem in space. This drives a lot of problems with space-based wavefront control. So the wavefront sensor is after the deformable mirror. So it's down here. So the light comes off the DM and goes to the wavefront sensor. And this is what we call a closed loop control system because the sensor sees the corrector. So essentially the wavefront sensor should eventually see 0. It should just see a flat wavefront coming through if everything's working perfectly. But it won't because nothing works perfectly. And so it sees this little change that it needs to make. And this control system then has to make a calculation. And stepping back for a second, remember this is a finite exposure time that you have to take. It can't be instantaneous. So there's already some time there from the beginning of the exposure to the end of the exposure. And I said kilohertz, we're talking milliseconds here, but that matters. And then this is a computer. It's probably a bunch of GPUs doing a bunch of matrix math. But that takes some finite amount of time, hundreds of microseconds. That matters. And then you have to send this over a network cable to this device. This device, which is the deformable mirror, then has to process the signals that got over the network cable, and then it has to move the mirror, which is some massive piece of glass. And by massive, I don't mean big, I just mean it has inertia. So that will take some time to move. So this whole problem, you're always late. We're always trying to catch up to the atmosphere as it's going by, and we call this servo lag. And even in space, this is a problem, and for reasons not having to do with speed so much as the faintness of the stars, of the signals we're detecting because of the smaller aberrations. But this is one of the key challenges, is making the system run fast. And to illustrate this, this is showing you a simulation of the atmosphere at Los Campanas Observatory. And this is a 7-layer atmosphere model, and if you stare real hard, you'll see different vectors going through because there's different phase screens that are being propagated here. This is a 2 kilohertz simulation, but I'm only showing you every 10th frame of that simulation. And right, this is a movie, so it's like 30 frames per second. So this is nowhere close to real time, but look how fast that's blowing, right? And so we have to take a measurement of that turbulence, get it applied to the deformable mirror in time to make a difference, and then do that all again, 1,000 times a second, all night, every night when we're observing. So a problem that I'm sort of glossing over in terms of how we do it on the ground, but it's pretty interesting in terms of how this will work in space if you're working on space-based wavefront control to try to correct these aberrations. That's that this math hides an interesting problem. And a way to illustrate that is, this is the same cosine aberration that I showed you before. This is the sine aberration that goes along with it. So it's basically the same wave, just phase shifted. And because this is the modulus squared of this Fourier transform, again, exercise for the student, I'm not going to go through this. But both of these aberrations produce the exact same pair of speckles, same brightness, same position in the image plane. And you can think of this as the problem being we detect photons, which are just the intensity, not the electric field. But to correct that aberration, we need to know the complete electric field. And this is a fundamental problem with detecting intensity. So if we just have those 2 speckles, you don't know the difference. You can't tell which one it is. If you guess and put this one on, all you did was, but it was actually this one, all you will have done is amplify the aberration, not correct it. But therein is a hint for how to solve this problem. You can just do that. And if it made it worse, you were wrong. If it made it better, you were right. And you just sort of walk through a collection of aberrations to try to find the right answer. And this is the fundamental thing used in something called speckle nulling. And there's a much more advanced version of that, usually just referred to as electric field conjugation or pairwise probing in ESC, where you do a set of probes and then do a bunch of math to solve for the electric field in the focal plane. And just to sort of illustrate what we're talking about here, this is what has to happen in a space telescope. And this is the continuation of that great video that NASA or JPL put together. So this is showing that going on with a DM in space on a coronagraphic space telescope. So what they're showing here, and they don't really illustrate the probing aspect, but just imagine it's going on. So there's a computer currently processing these images, and they're putting test shapes on the DM, solving for what the field is to put on the DM, and they dig this dark hole. So now they're correcting for all of those minute imperfections in the optics and finding these planets in what we call the dark hole. And so even in space, you have a closed loop wavefront control system using focal plane wavefront sensing that has to be working with a coronagraph to solve this problem. So let's move on and show a sort of what we could call an up and coming real example of an AO system. And this is MagAOX. I'm showing you this because this is my baby. This is a new extreme AO system that we're currently building to go on the Magellan Clay telescope. And our particular goal here is to optimize the system for visible coronography. So we want to take images of planets in visible light. And particularly our number 1 goal at the beginning is to do this at H alpha, the emission line of hydrogen that accreting planets emit. So in this bench that you see on the telescope here, there's 2,000 actuators. There's actually more actuators than that, but the main DM has 2,000 actuators And the whole thing's going to run at 3.6 kilohertz. So 3,600 times a second, we're going to take these measurements, turn it around, and apply it to the DM. And this is our awesome logo, because we're extreme. My grad students like to play pranks on me, and one of them thought that it would be a funny April Fool's joke to submit this logo for a design review, and I punished her by making her our graphics designer, and so she came up with this, and it's pretty cool. So zooming in, this is what MagAOX will look like. So this is just 2 meters across by 1 meter. So it's actually a pretty compact instrument if you're used to instruments on, if you've ever seen like a spectrograph on a telescope like this, they're usually gigantic. This is actually a very small optical table. A big electronics cabinet, this has, potentially could have over 100 teraflops of computing in it, plus all of the control electronics for, and camera readouts and everything. If we take that dust cover off, it's not actually, that's not vacuum or thermal control. It's really just to protect the system from dust, because remember, this is a telescope on a mountaintop that we open and leave open all night. If you zoom in, that's what it will look like. This is just a render of the design, but you can see how complicated this really gets and why we're obsessing over the fact that all of these optics are not perfect, because we need a lot of optics. There's something like 25 reflections off optics before it gets to our science cameras. So it comes in from the telescope. There's a whole bunch of stuff that goes on to prepare the beam for the main AO system, including there's a DM in there, what we call a woofer, that's a low order, very small number of actuators. Our high order DM is right here, goes down here to the lower level, and then there's this beam splitter that you saw in that video where the green light goes in here to our wavefront sensor. And this is our very special wavefront sensor camera that has very low read noise and can run at 3.6 kilohertz and feed those signals back up to the DM. The red light goes through the beam splitter and down here. This is a focal plane wavefront sensor, so that concept I showed you where you're measuring the intensity in the focal plane and trying to infer the electric field, we're doing that with this camera. And it's actually light rejected by that coronagraph, and I kind of glossed over that, but remember we put in that opaque mask and reject that starlight. That's actually useful information, and so we're capturing that with this camera. And so that's feeding it back to another DM that's actually right in here. And so we have 3 DMs on this table right now. There could be 4 later. And this is our science camera, which we also, these are high-speed EMCCDs, so they're low-noise detectors. So this is another place where we have potential signals that will feed back to these DMs using that same concept of focal plane wavefront sensing. This is a CAD drawing. This is actually what it looks like in my lab. This is actually out of date. We've started building the dust cover. As these things always go, the dust cover wasn't quite right, so we have to take it apart and drill some more holes. But this is basically the initial alignment of the system with some of the optics installed. They're not, a lot of those are just test flats. And so this is working, or it's a work in progress, but it's on its way. The key thing we don't have yet is the deformable mirror, which you don't see it up there. I expect it, every time I ask, it's another month, but I think it's another month from right now before we'll have that. I'll just give you a quick advertisement for some ongoing work and kind of show what I think we're going to be able to do with this system in terms of the control problem we're trying to solve. And for a long time, there's been a discussion of predictive control. So everything that I just talked about, I didn't really go into how the controllers work, but what all those examples I've shown so far, what they're really based on is you take a measurement and you just apply that one measurement as fast as you can. You just do that over and over again. You only ever use that one measurement in closed loop. But all of this information there's a lot more information there. And so that, you saw that video of the atmosphere blowing across the pupil. And you saw, clear shapes and patterns that were blowing across there. And all of this is really just this correlated noise, both spatially and temporally correlated. And that gives us a hint that there's information there that we can use to predict what the next command should be. And so many people have been working on this for a long time. Olivier Guillon and I have recently become pretty interested in this because of its impact on the contrast behind a coronagraph. Most work to date has been on, or a lot of work to date has just been on image quality. And that we're sort of extending some stuff that was pioneered by Lisa Poinier for GPI. And so this video is a simulation of a MagAOX-like system, kind of idealized, and this is kind of a contrived example. But what you're seeing here is you start out with an open loop system. We close the loop and you see that airy pattern. And then I put in a coronagraph. And so now you have this dark region and you see this swarm of speckles. And I've injected those 2-point sources there. And now I turn on this predictor. And I'm just using something called linear prediction, which is a power spectrum based statistical technique. If you need a buzzword, like everyone likes to say, we're doing machine learning. This is speech recognition, which is what where linear prediction really received a lot of attention a long time ago. Actually, we're like decades behind. But you can really see the power of doing this predictive control. And so we're working hard on figuring out how to apply techniques like this to coronagraphic systems. And this is probably going to be really important in space too, eventually. But you can see it just sweeps out the dark hole, and you see those planets that you can't see without that predictive controller. Okay, so where does this leave us? So AO systems are now in routine use. This isn't magic. This isn't something that we're hoping to do eventually. This is actually old news. So you've probably all heard of GPI and Sphere. There's also MagAO, LBTI, SkexAO. It's actually a very similar system to MagAOX that's working on Subaru right now. And all these are soon to be joined by MagAOX. And space coronagraphs are maturing very rapidly. We haven't really put one in space that performs at this level, but the W1st CGI effort has really advanced the state of the art here. And in the near future, we hope that it actually does some demonstrations of what this all could do. Long term, there's HABEX and LUVOIR, these huge observatories that are what we're going to actually need to take that 10 to the minus 10 image of a pale blue dot. So the key thing, though, is even with all this sophisticated wavefront sensing and control, we're always going to have speckles. They will always be with us, this residual starlight scattered on the image, and it's always going to be trying to fool us into thinking that we have planets. And so I'm just sort of setting up here for when you take your data at the telescope, what is the noise in the image? Now there's this hard problem of how we deal with it and how we interpret it, and that's I'm going to leave to other people to describe for you. This is just a very short list of further reading. I'm going to try to update this before we post this. I highly recommend from Jeremy Kasdan's 2014 Sagan Workshop lecture in this room 4 years ago. He goes through an in-depth discussion of wavefront propagation and explains to you all of the nasty details that I swept under the rug to get through this quickly. And then there's a bunch of fundamental papers that are worth looking at, and I'm going to update this because there's actually probably 10 more things that you should know about. So if you want to learn more about this, these are all good papers to look at. So that's all I have. Questions? Yep. Spiders are horrible. Yeah, so the question is, there's spider structure that supports the secondary mirror. And I never really showed you an image of a real telescope, but you can't just hang the secondary mirror over the primary. You have things holding onto it. And this is a very good question. Spiders are awful. They're horrific. Thankfully, in terms of the coronagraph, the W1st CGI, the coronagraph instrument on W1st, that effort, because of the nasty pupil on the W1st telescope, caused everyone to figure this problem out. So we actually are pretty good at constructing coronagraphs, but it takes a lot of work. You can't just use that simple Lyot diagram that I showed you. You have to put all kinds of very complicated structures at each one of those planes. And even on the ground, it matters. They do weird things, like a spider arm separates parts of the pupil. And so you have these independent islands that your wavefront sensor will try to drive to different points. And so you end up with horrible images if you're not careful. Real telescopes are nasty. They don't work like these contrived mathematical examples that I showed you.
You mentioned in your talk just now that the movement of the mirrors on the picometer scale yesterday, and how this is figured out, how the scale is less than a kilogram or a kilogram.
Well, I guess the answer is, the question is, we're talking about picometers, hundreds of atoms, and the RV spectrographs have the same problem, that the spectral shifts are sub-silicon atom size. And are we going to reach limits where we can't make these things smoother? We can't achieve these precisions? The answer is, of course, yes. We can't get to picometer smoothness. Amazingly, we can get to picometer stability. So we can control, we're pretty sure we can control parts of the telescope to picometer precision. And the RV spectrographs do achieve this subatomic detections of shifts, or are close to doing it. This is sort of glib and something that people commonly say when asked this question, but just look at LIGO. LIGO is actually achieving these precisions in an actual optical system, and we sort of have started saying that look, LIGO can handle it. So we know it can be done. These sorts of optical problems can be solved, but it is very hard. Right. So the question is, for all of our control systems on MagVOX, what contrast level do we expect to achieve? So the raw contrast, so just if you just took a single snapshot image, depending on star brightness and depending on how well our control algorithms work, could be anywhere from 10 to the minus 4 on just a typical star, like an 8th magnitude star. On a very bright star, we could actually maybe get to 10 to the minus 7 on a really good night. That's almost certainly not going to happen for a long time. There's a lot of work to get there. But that's just the residual atmospheric contrast. You also have to understand the optics, I sort of was just talking about optical services, but there's a parallel discussion about money and how much money you spend on having people polish your optics. So you always have a budget. It's your air budget and your financial budget, and our optics are spec'd to give us about 10 to the minus 5 without any wavefront control. And then with all that focal plane wavefront sensing control, because those polished in imperfections change slowly enough, I think that will just go away. It'll be negligible next to that residual atmosphere 10 to the minus 4 level. And that's just the raw contrast. Remember, I'm just talking about like a single snapshot. The post-process contrast could be as good as 10 to the minus 6 on a typical star without, after several hours of integration and all the hard work on post-processing that we're going to hear about soon.
So I know that traditionally, so direct imaging surveys like sometimes here actually have a lot of trouble detecting new exoplanets. And so I was wondering what kind of improvements
Yeah, so the question is, existing high contrast imaging instruments like DPI and Sphere, and we might as well just say things like NICI and the SDI survey before, and the IDPS, International Deep Planet Survey, have all not detected that many planets. And what's the difference with MagVOX? It's going to help us detect more planets. Well, so all of these surveys, and this is sort of a sweeping statement, so it's almost certainly wrong, but for the most part, these surveys have been looking at young, very large, giant planets that are still self-luminous. And I'll defer to Travis's talk, I think, for explaining exactly what I'm talking about here. But this is, they're looking in the infrared for the light emitted from these planets as they're still cooling down from formation. So rather than saying that our AO system is so much better and we have this technology that's going to work better, what we're doing is looking in a completely different regime. So for one, we're looking in H alpha, looking for accreting planets. So we're not banking on detecting these thermal photons. We're looking for photons from these very bright H alpha planets. Kate's probably going to talk about this in the near future, a little bit. Okay. And we're also, maybe everything works really well, we're going to try to look for reflected light from a small handful of giant planets that are very close to M stars. That's a long-range goal. But the key thing is we're trying to, instead of just trying to make an incremental improvement and do the same science, we're actually trying different science and trying to detect planets in different ways.
All right. think that's it for questions.